The main thing to kind of talk about initially, right, is like there's these two different things you'll hear about replicating data and like partitioning data. So just know that, like, um, give me one sec. I'm trying to share my. They changed the. I'm trying to do the whiteboard, but oh, there it is. Um, So basically, like replicating data is literally like the same rows of data. Like say we have like customers, Alan, Bob, and Charlie, right? It's literally duplicating that same data, okay? And you can imagine, so this is replication, okay? And you can imagine, like why would we want to do something like this? Well, there's like three, I guess, main reasons. So one is just like geography. So imagine you have customers, like maybe your banking application or something like that, and you have customers that live in different parts of the globe, or like, we need to bill somebody that lives in a different part of the globe, uh, right? Like we might, to make sure that there's like that we can be relatively fast with these transactions, right? We're going to want to be close to the customers. So we can literally have like one node or one server in the US and another one, somewhere in Asia, right? And that way the US customers get fed to the one in the US, the ones in Asia get fed to the ones, in Asia. And we're literally, like I said, we need the data to be consistent. So we duplicate all of the data, right? And how that gets kept up to sync, that's pretty complicated, and it varies based on the database. Uh, I doubt we won't spend too much time on that, except with, analytical databases. But right, like that one benefit of it, of actually just duplicating the data and replicating it, is geography. Another one is just like kind of, there's probably a better word for this, but like reliability. Um, Meaning, okay, if one of these nodes goes down, we still have a database running, right? That's pretty beneficial for us. And then the third one is, and so one is, still have a node running. And the other idea also is like, don't have data, right? Don't lose the data. The third benefit is throughput. This occurs both with like reads and writes to the data. So it's really actually like with transactional databases, it is very important with like writes, right? That you can like have lots of people tweet or post or whatever, and not have to like put them like wait and have to like have them all wait in line until we process it one by one, or at least make that very fast to do so. um, but also like with reads, right, being able to read the data quickly, that's also important. So if you think about it, we could just, if we just have various requests coming through here, and you don't want to have to like have them wait in line. So instead what we can do is just very simply, you could have like a load balancer, and then as a request comes through, if it sees that this database is currently overtaxed or like occupied, it can then just feed it to the other database, right? And here we just have two replicas, but you can imagine having a lot more replicas of the data. All right, so just remember, when I'm talking about replicating, it's not just the data here you're replicating. You really want to think of this as an entire computer, right? So it has the hard drive, it has like the memory, and it has the compute. Okay? So that throughput, right, becomes easier with more compute. Any questions about this so far, right? So this is kind of like data replication. Yeah, Conwall.
Yeah, Jeff. Wanted to quickly ask if this sort of replication is more useful and more efficient in select operations analytics, because I was thinking how the insert is essentially synced between different. database copies.
How it's synced?
How the insert or update operation is synced between these
Yeah, so it
instances.
depends on the database, and it is complicated, right? So, like, really, what these databases do is they can have different kind of techniques for how to update the database, for how to update these like distributed nodes. But node with an analytics database, and this is kind of I think what you're getting to, replication, like in the analytics context, replication is actually not so challenging or emphasized by the analytical databases. And the reason why is because if you think about it, so what Conwell is pointing out is that basically there's this challenge of what they call like available and consistent, okay, across, uh, you know, if I really want to emphasize it, across partition data, which you guys may have heard of as like the CAP theorem. I'm like stretching it a little bit, but really the idea is you can't both have data that's you can't both have your database be fully available and consistent across nodes because it takes time. Let's say we write to one of these nodes, it takes time to propagate those changes over to the other node, right? So what they'll do typically is if someone writes to say like update Charlie, update his birthday, that row record will be locked until the other, and there's different ways of doing that, until the other node has the data to be able to read from it, right? That way, like if you give like the example of like a banking application, let's say we withdraw money from Charlie's account, right? And then his wife is, over there and she also withdraws money from Charlie's account. Now they just got away with maybe some extra money, right? So what they need to do is you need to lock down that row before the withdrawal has been propagated to the other nodes. Something like that. Okay? So again, how that occurs, that's a design decision that varies based on the database. We can go into that maybe in another lecture if you guys are curious about it. But that's very important with transactional databases. Why? Because we want our consistency, but transactional databases are facing customers. It needs to be high. The data we want these to be highly available. With analytics databases, the high availability and consistency is not a big deal. Because if you think about it, what are we doing? Oftentimes we're just batch loading our data anyway. So we can wait, like this only takes like a second or, if across the globe, maybe it takes like a few seconds. But we can just wait until the data is kind of like in sync before we like perform an analytical query on it. And that's not such a big deal. So like if you research like what does Redshift do with replication, it's not even really mentioned. Like I've researched it and it's really not even mentioned because it's not a big deal. Like it's not really a challenge that we have to deal with in analytics because we don't have this issue of having to have our data both available and consistent. The other thing you can think about is like geography. That's not really such a big issue. Like with analytics, like we don't really, we typically our teams are pretty co-located, so you typically don't have to replicate it based on that reason. We can just like choose a central location. Now this might be different with something like Amazon, but even then they probably have different subsets of the data for different analytics teams, and it's fine. So really the only thing that we care about is like not losing our data, and that we can achieve by just like taking snapshots of the data. So again, like with analytics databases, replication actually does not come up that often. It does, I'll point it out when it does, we do see it, but instead you more see this with like transactional databases. Like as you go through, and I wanted to, I guess, like just distinguish, cover this and distinguish it between partitioning. And partitioning you do see a lot in analytics databases. Did that answer your question? I think that answered or got to your question, Conwell. Yeah.
Yes, thank you.
All right. So then the next thing is partitioning the data. So partitioning the data is different, right? Here we're not necessarily replicating the data. Instead, and there's two different ways of partitioning the data. One is literally, and some people don't distinguish between this at all, but one is partitioning, and then there's something called sharding. With partitioning, you're slicing the data or splitting up the data across. You're just clustering it together. So this can be on basically different. In Redshifts, it's called like data blocks, but it's different parts of a disk, basically, or it could be separate disks. But it's different parts of the disk. And so let's say we have, oftentimes it's done by date. And so let's say we have like all the 1990 sales on this partition and all the 1991 sales on this partition. Okay, so then when we say like look at like average revenue in 1991, we don't have to scan. This comes in. We don't have to scan through this data block at all, right? This partition of the data at all. All right. Instead, we can just go directly to this one, and so that saves a good amount of time. All right. So basically, this can help us avoid scanning through the entire data set by partitioning the data and grouping it together. So the data physically lives in a similar spot on disk, and that makes it faster to read. All right. So this is partitioning the data. With sharding the data, here the data can live. It just means that it's partitioned across multiple nodes. So with something like Redshift, it actually partitions and shards, meaning that the data is both like partitioned within a single node or a single like database server, but then also split, and you can determine how many across multiple servers. So again, like you can split, say you partition by year. So here's 92 and here's 93, right? And the request comes in and say we, want to look at the average of 93, it will go to this partition. Or let's say we want to look at, so again, like one benefit, let's just pause here. One benefit of partitioning is, kind of like fast lookups, right? Kind of almost like similar to indexing, but one thing that's different from indexing is with indexing, the data doesn't have to live in a specific location, right? With partitioning, the data gets written to different locations based on a value in the column, right? What's the second benefit? It's again, like you can think of like this division of labor benefit, meaning like, if a request comes in, we're looking just for 1993 data, then another request comes in, if it happens to be looking for 1991, right? Like we're not taxing the same node twice, right at the same time. So we can serve both those requests simultaneously. One last thing that we'll see, and we'll get into this more in a second with Redshift, is parallel processing. Maybe we should wait. I'll just say it briefly now. If it doesn't make sense, I'll go through it again in a second. Let's say we want to know what's the average amount of sales across, total, right? Typically, with just one computer, we'd have to, we have to scan through all the data, right, and calculate the average. With however, like sharding it, what we can do is we can calculate the average across all the data on this node. And let's say there's 10 rows of data, and total sales is like, let's say 120. So average sales is 12 with 10 rows. And let's say there's, 20 rows of data over here, 20 rows of data. Average sales is like 240 per year. Or total sales is 240. So that means it's 24 across 20 rows. And then we can just combine, to get the total, to get the, right? So basically we can compute the average on this node, compute the average on this node, and then send back the results to typically like this thing called a leader node, and then it can combine, basically ask each node, what's your average, how many rows, what's your average, how many rows, gets back those answers, and then can compute a weighted average, which is just like, man, it's something like, I think you have to take the total, so it should be, I think there's a total of 30, what do we say, 36 rows, so it's going to be 0.33 times by 10 is the average, plus 0.66 times by 24, right? And that'll be the total average. And just notice, like, this doesn't work only with average. It also works as like with maxes, right? We can find the max across this node, find the max across this node, and then find the max across, right? Compare the max values across both nodes. So this works like a lot, this kind of procedure. And so it allows us to do this parallel processing. And then the final thing is just know, like, oftentimes this parallel processing isn't just based on the number of shards, but on number of partitions of the data. And the reason why, as we'll see with Redshift, is because each partition of the data can be allocated a separate core of CPU. So basically, like, the amount of the number of processes you're able to run in parallel on a computer is based on the number of cores. I forget what's typical in a Mac. Maybe it's like 4 cores or 8 cores. So what that means is if you have 8 partitions of the data, you can compute 8 queries, right, at once, simultaneously on a single machine, right? So you can kind of like, split this up into 8 just on this one node and another 8 partitions based on this node too. Okay, so again, you get to like perform parallel processing and then ask each one to send back their average and the number of rows, and then calculate the total overall. All right, so this is kind of a big deal, especially with Redshift. But even without this, you still get this. If we're just asking about 1992, cool. Just this one CPU can handle, or this one core can handle it. If we're just asking about 1993, great. Doesn't even touch this computer, right? And we can kind of answer those questions simultaneously. And then finally, right, like we said, fast lookups. Okay, so this does happen all the time. This happens with Redshift. This happens with Snowflake. I believe this happens with PySpark too. So it happens all the time. And we even saw partitioning, if you remember, and I actually put back in those readings just so you can see it again. We saw it with like bucketing our data with S3, that we would partition the data into like different sections based on the year of the sale. Hold on. Let me see. Okay, what's the difference? So not clear the difference between shards and partitioning. Partitioning, one computer. Here, if you get rid of this guy and you just have one computer and you split up the data, that's partitioning. Sharding the data means split up across multiple computers. Okay? Typically with sharding the data, or the way Redshift works, there's a leader node. So the leader node comes in a query. Someone says, tell me the average number of sales. That gets split sent off to each one of these nodes, comes back together, and then this leader node gives back the user the final answer. All right? So that's sharding the data, is just splitting across multiple nodes. This is something people like distinguish and worry about, because actually what oftentimes takes a lot of time is not the computing, but actually sending the data across the wires, like that. The network latency is oftentimes one of the most costly parts of these requests. Okay, so like in waiting to hear back from each one of the nodes that might be relevant, right? That can take time. Okay, let me see if there were other questions. Yeah, and then remember, partitioning versus indexing, kind of similar, right? In the sense of like helps with fast lookups. But with indexing, the data can live literally anywhere. With partitioning, we want to store it in the same spot. Okay. I think that's mainly it for that concept. Let me, hold on, can I, let's close the whiteboard. Let me see what else I want to, I'm sharing this again. Share, oh, screens. Okay. Let's see. So we actually cover it, right? Why replication, durability, geography, throughput, right? Just literally duplicating the data. Right? If we lose it, we have another node where it's still available. Geography, we talked about that. Partitioning, right? We said, partitioning is basically on one machine. Don't have to look through all the rows, just have to look through the partitions. Sharding across multiple machines, right? Another thing I didn't mention is why might we need to shard the data? We just literally might not have enough space on one machine, right? Like, yeah, that's another reason. And then finally, just like distribution of work. Let me see. It looks like there might have been one more question. So the first strategy is to partition the data. If the system scores are not enough, then you can use sharding. Yes, that's true. And it depends on, not every database will take advantage of this like parallel processing. They will, like for instance, partitioning is available on Postgres. Okay, and what is the benefit on Postgres? Like basically fast lookups. Even with Postgres single node, it's not smart enough, I don't think, to allocate different. I might be wrong about this, but I just haven't heard of that Postgres will allocate different cores and do parallel processing. That doesn't sound right to me. But what it will do is say, okay, if you're just looking for, the average sales, in 1999, it will just go to that one partition if you have partitioned on that column on the year. And how do you do that? I have it right here. Create table sales, blah, blah, partition by, and then you can do like, you literally, there's different kind of ways to partition, but here it's range sales date. That works fine. Okay. Cool. Next thing, we can get into how Redshift works. So I always like to start with like, and I have it in my notes actually. Give me 1 second. Yeah, this is better. Okay, so I always like to start with like the problem, which is, there used to be, and there still are, Oracle databases, but like in the 90s, this is how they were designed, was like if you were an analyst that used like, Oracle, and, maybe all the company data was stored, the way it worked is you would have your computer, and each analyst has their own computer, and the computer would query a central data store. Okay, this is called like shared everything storage, right? Because every query is, and all this CPU, right, is it's responsible for data, any request, and really more importantly, any part. There is no partition, any partition of the data. Okay, right? Like there's only one CPU, one set of memory that's handling this. So as you imagine, like this actually does not scale very well, right? Because you can add more CPU, but it's not linear scaling here. You would have to have decided that up front. So as you got more data, and as more requests are coming in, this is probably not very useful. Instead, the way that Redshift works is that as you run out of space, basically on your computer, you have to add more nodes. Okay, so what that means is, each CPU, each computer, you can see I have this node 1, node 2, node 3, node 4. Each computer, each node is only responsible for its subset of the data. All right, so this is kind of like naturally scaling. One way of wording is shared nothing storage, because each set of resources is responsible for its own data, right? You're not going to borrow resources from over here, obviously, to make a query over there. That doesn't make sense. So this is like shared nothing storage, and it naturally scales. It scales linearly, which, as we'll see, may or may not be the best thing, right? One downside of this is like, well, even if maybe you don't want more CPU power, you might have to buy it, right? So Redshift can actually add up in cost, right? So you might really just want to pay for more data storage. And now they've changed the design, they've made it easier, but just, there are other databases designed similarly. One issue with this just strategy of share nothing storage is that it scales linearly, but the most important part is the CPU and memory that you're paying for. That's the most costly part, whereas you may be buying additional nodes just to store more data, right? So it's like you don't really need this more expensive part, potentially, but you're buying it because you need to place the data somewhere. So that's the downside of Redshift, and we'll get into like how you can get around that later. But again, like, how does this help us? Helps us with all the ways that we talked about, right? That we can get the distribution of work. If all the data is on one partition, then one single node can handle it, while other nodes can handle other requests. Faster lookup. If we know that you're looking for like data, this is movie data. If it's in 2008, we don't have to look everywhere. Just look at the spot it's located. And then finally, parallel processing. So I did that for like, this. Here I gave the example here of the parallel processing. If someone says, give me the average year across my movies data set, we compute the average in parallel across each partition of the data and then send back the response to the leader node, and it will then combine that to a weighted average to give the user the end result. Okay. The other thing you can see is just terminology. The terminology can vary, but you will hear, I think more typical nowadays is like leader node, and then Redshift calls all these compute nodes. So the leader node will have information about like what data is where, right? It's a kind of like indexing basically of these partitions. So it knows, okay, you're looking for 1999 data, better go over wherever here, 2005 data, better go over here, right? It knows, it has an index, basically a table lookup saying where does all this data, where do all these partitions live, and it directs what query should it send to each node, and then when it's done, may have to combine the results before sending it back to the user. All right, so that's what the leader node does. It kind of like coordinates, right, or directs the computations of the other nodes. And notice that it does not have any data on it. Other thing, I guess I don't have this quite yet. We'll get into other benefits of Redshift. It does a couple other things than this, but this is kind of what makes it unique among different analytics databases, is just this architecture. And like I said, it does have pros, like 10 years ago or so, like not even 10 years, maybe more like 5-6 years ago, honestly, 2017. Like every data science team basically used Redshift. Like immediately, like everyone used Redshift. It was like Snowflake was not popular yet. This was basically what everyone used, and it was expensive, right? But the benefit of it was it would scale, right? Nowadays, as we'll see, there are competing. Snowflake is the main one. Snowflake doesn't have this issue of while you add more data, you're paying for more compute. Right, so we'll get to that later. Cool. Let's see, I think there was a question. Okay, regarding sharding, how would it actually look in terms of architecture? Would it be a hierarchy schema where if I do a query, it would connect to other tables and then would retrieve other tables that would be better under the main child nodes and then retrieve my query? So you can see an example of it, Alan, here. I don't know if this kind of... Do you want to maybe ask your question in context of this, or does this clarify it?
You did clarify it, actually.
Okay.
So
okay, perfect. Yeah, this is how it works. And this is how, I should say, this is how it works with Redshift. Other databases, there's something called like multi-leader. So you may right, because maybe you have this issue of, you have everybody now. This becomes the roadblock, right? This becomes the bottleneck. Right, so there's also like multi-leader databases where you have a second leader, and that can also direct, right, and maybe also coordinate with this one. So there are fancier architectures that other databases will use. This is what Redshift uses. Cool. The next thing is just like column-based. We can just go into this. I think we've talked about column-based storage, but it's worth reviewing. Actually, I'll move to my notes. So just remember transactional databases. If you think about like Facebook, right? You click on someone's profile, you're getting like everything from his profile, right? His name, his photo, his birthday, whatever, interests. So the whole row of data is basically displayed. But with an analytics database, right, we're analyzing the data. So typically one row of data isn't going to cut it. For us, we want to know like what's the average runtime across all movies or all movies in 1994 or something like that, right? All users more typically, right? One user is not what we're after. So this has implications for how the data is stored because the way that this really made sense for me, if you think of like a hard drive as like a record, right? Because that's what the disk looks like. It looks like a record, and then this is just like a string of data, that's like around. Right, it's a tape, really. So this is like the data is just linearly on that tape in the hard drive. So we have decisions as to how to organize that data, sequentially on that tape. In row-based storage, where it's sequential, one row at a time. Meaning, here's all the information about Pulp Fiction, 1994, number of minutes, who produced it. Then here's all the information about Titanic. Then here's all the information about Avatar. Right? This makes sense because I can just read this data when someone wants to know about Pulp Fiction, and we pull it all out, load it into memory. In something like Postgres, you have to read at minimum one page at a time. So even if you're only looking for Pulp Fiction, one thing to know is that you may be getting extra data, right? That's kind of on that page. But, right, if you kind of have the same concept of pages, and now we're working with analytics databases, we want it to be organized in terms of columns, okay? With Redshift, this is called like a data block, right? So what's stored sequentially is all the years, okay? And there is a way, obviously, for them to connect it to the, to the attributes around the row. But we can just read literally one column of data and not have to load up, right, the rest of the attributes. Whereas with row-based storage, we would have to do that, right? If I want to get the average year, I have to read in all this data just to get the 1994, 1997, and 2009. So that's a problem. One, because we now have to jump around, right? We have to read more data, right? Because this good stuff is now spread out, right? Two, we have to load it into memory. So we may run out of memory. If you run out of memory, typically with analytical databases, it won't just break, but what it will do is it will rewrite to disk. It will save part of the results to disk, and then have to read that from disk, and that can take a lot of time. So with column-based storage, right, we don't have to read all this extra data into memory. So that's another big benefit. I'm trying to think if there's anything else. Those are the main, and it's all together. Like the data's all together. So it's like all the 1990. Especially if it's sorted, we can just load up, read all this data. It's kind of right there, sequentially there, so we don't have to jump around on the disk either, which makes things easier. There are additional benefits of column-based storage that we get to do. So that comes to compression and zone maps. So compression, you can see, like I did put in this query, analyze the compression. I think of this listing table, and it showed me that the estimated reduction, these are just ID columns. I don't know why I guess it depends on the values, but it was like estimated here was like 75%, like 30%, or like to like 60% compression is like, you can kind of expect that lots of times. So we're literally being able to compress more efficiently with column-based storage than with row-based storage as well. One reason why for that is the compression algorithm. Like you can do compression with with like something like Postgres, but it's compressing the entire page of the data. And because these are of different data types, it's not as efficient in terms of condensing that data. Like it's harder to kind of express in a compression algorithm what a string represents versus what a number represents. When the data is all the same type, that compression becomes a lot more efficient. So that's one benefit. Another thing is what's called zone maps. With zone maps, all that happens is for each data block, let's say this is a data block, Redshift will also store what's the minimum and maximum value in that data block. For here, it's 2017 is the max, right? And 1994 is the min. So if someone asks me for, the average runtime in 1993, we'll just skip this data block altogether. Okay? So notice the data does not have to be sorted. We don't have to do anything with it. It's just literally going to take what is the max, what is the min, and it just happens that 1993 is not in there, so we can skip it, right? So that's another kind of benefit of column-based storage, and that kind of Redshift takes advantage of is zone maps. So you can see, we do get a lot of benefits out of column-based storage, right? We get to read less into memory. Our data's in one place. We get to compress the data. So all those things help speed up the request, and also we get compression, so it takes less time. And then we also get these zone maps things. So that's very, very useful. In almost all, I think basically all analytical databases you can basically assume that they are using column-based storage. They might not all have zone maps, but almost all of them are going to have compression too. Let me see if there's anything else to talk about. That may be it. There's so I'll deploy this stuff, data replication, partitioning and glue. You can just kind of read through this, and then partitioning strategy I think is probably useful too.